visiting us from the University of Arizona. He's going to talk about monopole walls, quantum field theories, and 5D, and melting crystals.
So the story which I will talk about today has to do with trying to understand a paper from mid-90s written by Cypher and Morrison. So I finally understood it. So let me start from afar with one of possible reasons to explore this. One might be interested in studying gravitational instantons. They were first introduced, I believe, by Hawking and Gibbons, in trying to study Euclidean quantum gravity. They're interesting in their own right. So these are Riemannian four manifolds with cell-dual curvature. Once the curvature is cell-dual, it automatically solves vacuum Einstein equations. And will also require that the Chern number is finite, so you have finite amount of curvature in space. Now there's only two compact gravitational instantons, T4, which we know, and K3, for which we don't know a single metric. So if one is trying to find these metrics on K3, one might try to start ascent with something easier and drop the compactness. And in a way, one can distinguish different spaces, different cell-dual gravitational instantons, by their asymptotics. So you pick a point inside of the manifold, look at a large ball of disk radius r, and you ask how large does the volume grow as r goes to infinity. So if it grows as r to the fourth, I'll call these spaces of ALE type. If it grows as r cubed, I'll call these spaces ALF. If it grows, well, any power greatly equal to 2, but less than 3, I call them ALG, and anything below 2 is ALH. So one can view this as approximations to K. One of the ways of approaching this problem, instead of head-on trying to solve this equation, is to realize this as moduli spaces of something else, and then use that realization to extract the metric. So this what was successfully done for ALE cases by Kronheimer. For ALF spaces, this can be done by studying moduli spaces, realizing them as moduli spaces of monopoles. So in the first case, you can think of this as moduli spaces of instantons. Now, if you look at moduli spaces of periodic monopoles, so these are monopoles on three-dimensional space which are periodic under shifts in one direction, then their moduli spaces are ALG type. And if you look at doubly periodic monopoles, or monopole walls, which I'll talk about today, then you get ALH spaces. And intuitively, you can think of a monopole having 3 coordinates in space and 1 electric phase associated to it. So that's why, for example, moduli spaces of monopoles are, roughly speaking, spaces with 3 non-compact directions and 1 compact direction. And the periodic monopole will require extra compact direction. So these spaces asymptotically, you can think of the end looking as r plus across a 3 torus. One of the direction of the 3 torus is the phase, and the other 2 is the position of the monopoles, directions. The way one studies this, one might try to study this, is through Nav transform. So Nav transform usually simplifies the problem quite a bit. For instantons, this was the original ADHM transform, which transcribes solutions of PDEs in 4 dimensions to just matrix equations. So the spaces now become moduli spaces of quivers, of quiver branches. For monopoles, Nav transform gives a system of Nav equations, so bows. And these are solutions of ordinary differential equations, so nonlinear. Still much simpler than these 3 dimensions. For periodic monopoles, you end up with slings, or kitchen systems. And again, you trade something 3-dimensional for something 2-dimensional, so it might be a little simpler. But once we get to ALH spaces, Nav transform takes us back to another doubly periodic monopole. So we don't have a simplification here, we really have to face the wall and study monopole walls. But some other things. Yes.
Was that really K3 or was it look like K2, the month?
What? Oh yeah, you're right. So very good point. So the picture here is K2. I said that this is approximation.
Sorry for that.
No, that's a very So, what is a monopole wall? W periodic monopole. To look at solutions of the Bogomolny equation, that is, we have our space, which is R cross the torus. I'll take the torus to be just rectangular, and square. We have an n-dimensional permission bundle of this, and we look at connection on that bundle, gauge potential A, and the Higgs field phi, and the morphism of the bundle. And the Bogomolny equation tells us that the curvature, or the field strength of this connection, is dual to the gradient of the Higgs field. The simplest solution is abelian case. So let's look at abelian connection and abelian Higgs field. So you can think of phi as just a function, real valued function, and little a as the 1 mole. Then the Bogomolny equation tells us that d phi, the electric field, or I guess the magnetic field in this case, equals to a gradient of phi. So if you hit it with another differential, it follows that your phi is a harmonic function. So how many harmonic functions do we have on 2 cross R? Well, many. So we expand them along the torus. But whenever you have any dependence on periodic coordinates, then your solution will grow asymptotically, either in exponentially, either in one direction or that. So if you want to avoid the exponential growth, the only harmonic function that you have is z. And this is a constant energy solution. You can see that gradient of this function is constant. So you basically have constant magnetic flux through the torus. But what's important for us is that there are parameters in this solution. First, there is Q, which is the charge or magnetic flux through the torus. So this Q will have to be an energy. Second, there is a subleading term, in a real constant, and here. And then when you have your gauge potential, the gauge potential can have some monitoring around the periodic direction of the torus. So there are these 2 other coordinates, P and Q, which are periodic. So you have 2 periodic parameters and 1 real, and also an integer. Now, this integer is charge, and these are the Fourier loops around periodic directions. Next, we can look at Dirac solution in R3, which is given by 1 over R function. And what we can do is we can arrange them doubly periodically. So you pick z equals 0, and in x and y, you can have a lattice of vertices. So this lattice with coordinates j, k, and 0, j and k. So let's put Dirac monopole at each of these vertices. So our phi is the sum of 1 over r terms, where rjk is the distance from where we are to jk known in the lattice. Now that will diverge. So we have to subtract some constants here, regularize the sum slightly. As a result, you get a convergent sum. And for each of them, you can just, it's a linear problem, you superimpose the gauge potentials. What is important here is that as you go to the left or to the right, so when z is very small and negative, or when z is very large, you can see what charge this corresponds to. And just as expected, on r cross t2, we have 1 unit of charge sitting at 0. So on the left, magnetic flux is 0, on the right, magnetic flux is 1. So that's a simple abelian solution. There is a cheap way of getting to U2 solution over this, so SU2 solution over that. You can take a constant energy solution and just multiply it by sigma 3 we don't gain anything, but in a way one can study now deformation around this. exercise with Richard Boyd to compare with our general story, which I'll talk about today. So once we saw these examples, we can get to the general problem. So we look for a non-abelian, for UN monopole. We need to impose some conditions at plus and minus infinity. And what we are saying is that as you go to plus infinity or minus infinity, your solution splits into these abelian solutions. So we require that eigenvalues of the Higgs field grow most linearly with Z. So we get this expansion. And you fix the charges Q. In a second we'll see that these have to be rational numbers. And subleading to the terms M. Now, once your eigenvalues of phi split, your bundle splits into subbundles. And that means that asymptotic eigenvalues of holonomy also split. So we fix eigenvalues of holonomy around the periodic directions of the tilts as we go far to the right or far to the left. A priori, there's no relation between these charges and data with plus subscripts. As you go to far to the right or far to the left, they can differ. And it's exactly this difference which tells us that there is some non-trivial non-abelian solution in between. Now let's look at the charges. If you look at the charge, so you can look at the flux through the torus. So you trace M, integrate over the torus. Because of Bergamoni equation, that's trace over the gradient of phi. Now gradient of phi itself is proportional to Q, because phi is B. And trace gives the rank of the function, just the number of eigenvalues with that behavior in front. So that number has to be integer. And the conclusion is that the charge is a rational number, and that the rank is proportional to the denominator of Q.
How do I say the charge is conserved between non-abilities?
It's not conserved at all. We simply go very far away to the right, and we impose the condition that to the right everything splits into these abelian cases. And then we look at one abelian block. So for that block the charge has to be integer. So next, to make life a little more interesting and a little more symmetric, we will also allow some Dirac singularities. So we pick some point in our space, and we allow Higgs field to have one eigenvalue which shoots off to plus or minus infinity. If you like, you can study a problem with no singularities, but as I said, story is a little bit more symmetric if you allow for singularities. So in a way, our complete boundary data in the problem is fixing Q's and M's, and P's and Q's as you go far to the left or far to the right, and fixing these points R plus or R minus, where you have Dirac singularities. So the first statement is that if you fix this boundary data, then the moduli space of solutions, the solutions of your equation modulo Gaussian summations, is finite dimensional, and it has hypercalorimetric number. So we would like to identify the moduli and know the dimension of the space. Next, once you've done this, for each set of boundary data that you fixed, you have some geometry of the moduli space. Now you ask, what if you change this boundary data? How does geometry change? For example, if you change all m's by adding a constant, that is, you add a common constant to the Higgs field, moduli spaces will not change at all. Or if you take your solution and shift it to the left, moduli space will not change at all. So there are some combinations of this data, or this boundary data, which are irrelevant for the moduli space problem, and some which are relevant. So we'd like to know which are relevant and how many are. Yes?
Do you need the Dirac singularities in order to have much more?
No, I don't. I introduced Dirac singularities, as you'll see later, to have some larger symmetry axiomal with moduli space. But you have a well-posed problem without it. Moreover, for some combinations of boundary data, moduli space will be empty, and we'll find the conditions. So let me give some motivation for what's to come. In a way, I presented this as looking for some moduli spaces which solve some GR problem for us. But another motivation is trying to understand these 5-dimensional quantum theories that Sergey collaborators will study. So one way of realizing monopoles in in string theory is by looking at d branes and looking at dimension 2 lower d branes which end on that. So let's say we have d5 and then we have d3 which ends on it with one dimension, one direction being relative transverse, one direction of d3 being relative transverse. So then the end of d3 generates a magnetic charge in the region of d5. This picture is quite useful if you just want to understand geometry or noun transform, for example, for conventional monopoles. But it's also useful in this case. So in our case, monopole leads in this directions, 3, 4, and 5. And we're interested in W-periodic monopoles, so 4 and 5 will be periodic. Once you have some periodic directions within the brain, you just can't wait to visualize them and see what other realizations of the system you have. So in our case, first of all, we can lift this whole story to M theory direction. So if you tubularize one direction here, direction 5, and S dualize, then you end up with this configuration which lifts. So the advantage of this, the reason for S duality and all, is that this lifts to a single M5 wrapped in a curve. And you can trace what this curve is. This curve will be defined in a minute using just the gauge theory itself. But this curve knows a lot about the modulus space. So in a way, this problem of monopole dynamics here is equivalent to the problem of M5 wrapped in a curve. This gives a nice way of computing, for example, asymptotics of these modulus spaces. And as you'll see in a second, also computing dimensions of relevant modules. Another interesting thing is that in a way, you end up with M theory on the 3 torus. There's 3 periodic directions here. That theory has huge symmetry. SL3Z cross SL2Z. That gives a very large set of equivalents of configurations, some of which can be interpreted as monopoles. So that is something to be explored, and I assembled relevant information in the next slide. But if you're interested in gauge theories, then you can see that there is another equivalent configuration. So if you t-dualize both of these directions, you end up with this theory, where now you end up with gauge theory living in these 3 dimensions. So living in these 5 dimensions, 1, 2, 3. So 1, 0, 1, 2, 4, 5. So it's a 5-dimensional theory, 2 directions being torus. And you can view this as a theory on a PQ network of branes. That is the theory that effectively Sergey is studying. And there is an electric-magnetic dual of that where you change P and Q. Simply change the role of 4 and 5 direction. So as I said, the advantage of this M theory view is that it has lots of symmetries. That you have M theory with 3 circles, and you can reshuffle the circles, for example, or you can perform any SL3Z transformation on the circle. These transformations act fairly non-trivially on these type 2B configurations that I just described. So if you look at all possible ways of compactifying, of reinterpreting M theory on 3 torus in terms of 2A, or in terms of 2B theories, you get this diagram. And I'm sure this diagram appeared somewhere in homological algebra. Just need to find where. It's quite natural. In addition to this SL3Z, which reshuffles the circle, there is another SL2Z, which acts like this, which acts as a mirror reflection here. As there is another M theory realization of this. So what we are doing is we compactify, for example, on the first circle and then on the second circle. So we compactified on circle A, that's what this arrow means. Then we do T-duality along circle E. Then we have 2 circles, we can change their order, and now we can T-dualize the second circle and lift up the M theory. We get a different theory. So you can track all the parameters, and then you can take various limits. Some of these limits that, in terms of gauge theory that I'm going to describe, give nice limits or degenerations of the SAM theory. So one of the circles here will open up while the other collapses here. This gives you reinterpretation of decompacted paradigm theory in terms of some 2A. So for us, we are limiting ourselves to just monopole story. But in principle, this diagram with all these relations between periods of the circle and Planck lines allows one to explore different limits. And all this diagram does is assembles the known rules, known correspondence between M theory interpretation and 2A and T duality and S duality. So let's go back to gauge theory and just describe everything without any appeal to M theory and these mysterious dualities. So if you start with the harmonic equation, you can write it as one complex equation and one real. So this is 3 equations. Then there's D1, 5, D2, D3, 5. You can assemble D3 and D2 into this complex equation. Then if you just look at the first equation, it implies that holonomy of phi. So if you look at this operator, which is modified parallel transport, modified covariant derivative along x. You can look at equation dx plus I phi d equals 0. So that gives you some holonomy in that direction. And this first equation tells you that eigenvalues of that holonomy are holomorphic functions of the remaining coordinates of this. So if you look at eigenvalues of holonomy as a function of this s, of the remaining 2 coordinates, you get a curve. And you can view this curve as just vanishing of characteristics polynomial of holonomy. So this is what we call spectral curve. This is exactly the curve that M5 is wrapped on. And you can see that to define this curve, I had to single out one of the directions of the torus. Okay, so I took direction x, for example, I pick some point, and I look at parallel transport along x direction. So taking values of that parallel transport depend holomorphically on the remaining 2 directions. Now, because this is curve of eigenvalues, each eigenvalue comes with its own eigenspace. So strictly speaking, you get an eigensheaf of that. But in this case, so long as sigma x is non-degenerate, you get an eigenline bundle over that. And the first statement is that this pair, curve and line bundle over it, is equivalent to the solution. It's 1 to 1. You could have chosen the other direction and studied, since you have 2 periodic directions, you can study holonomy in the y direction. And this will give a different spectral curve with a different line bundle. So there is this mysterious 1 to 1 map in between. And in terms of our previous M theory diagram, it maps one M theory on the curve, M5 on the curve, to the dual SL2Z dual M theory on a different curve. Now, this curve is algebraic due to the careful boundary conditions. So you can write this, if you multiply by a common denominator, as some polynomial, this vanishing of some polynomial of S and T. T is the eigenvalue and S is this holonomial. Yes?
Have you used the second equation anywhere yet?
No. I do need the second equation to argue that this is equivalent to that. So it's usual donuts enough. You need to argue that on the orbit of the complexified gauge transformation, there is only one solution to this equation. So here enters Newton polygon. At first, in this description, you can see that moduli of monopole wall come in 2 kinds. You can change the curve. There are moduli of the curve, and there are moduli of this line. So if you have a polynomial of S and T, which gives you the curve, it has a corresponding Newton polygon. So what is Newton polygon? You look at your curve, write it out. It has various monomials with various coefficients. They don't have to be the way you wrote it. That is an example for this simple solution that we gave before. But usually you get some polynomial. If it has a monomial with non-zero coefficient with powers mn, then you mark the corresponding point with coordinates mn on the lattice. You mark all points, all non-zero, corresponding to non-zero monomials. And then Newton polygon is the minimal convex integer polygon containing all these points. You can see this, that there is one point missing here. So if you wrote this solution, there is this curve, there is this Newton polygon, but inside there is one point, and it corresponds to ST term here, which is missing. So in general, you have this curve which has exactly the same Newton polygon. You have this polynomial which has the same Newton polygon. So what's the meaning of different parts of the Newton polygon? First, if you look at the edge of a Newton polygon, that tells you how S and T are related when they're very large. In other words, if you look at this edge with slope alpha beta, then if you look at polynomial along these, at monomials along this edge, they assemble into this form. There will be some particular monomial, let's say, corresponding to this point. But the rest is polynomial of this combination, which is determined by the slope. And moreover, this will be the leading part in the asymptotic corresponding to this edge. So when S and T are large, the rest of your algebraic equation is not important. So it tells you that when S and T are very large, this has to vanish. That means that this combination of S and T, of log X and log T, has to be a root of this polynomial H polynomial. From this you can see that there is linear dependence between log S and log T, and that means that the charge of your monopole problem is just alpha over beta. That slopes of your Newton polygon give you the charges of your monopole problem. Moreover, the subleading terms and monodromies are given in terms of these roots of this polynomial. So that's why if you take Newton polygon and you assign these numbers to it, so positions of negative singularities here, position of positive there, and this combination's ham of subleading term in Higgs field and whole number. This is what I call Press-Newton polygon, and that encodes the monopole boundary data. And then what you're allowed to do, you're asking how can you vary the curve, how can you change your polynomial without changing the boundary data? Well, it means that you can change all the coefficients corresponding to internal points, and none of the asymptotics will change. So you can count the number of moduli, just the number of internal points. That's the number of complex moduli. We also have moduli of the line bundle over that curve. If somebody gives you a curve, how many moduli does a line bundle have? In other words, you have electric field on the curve, or let's say magnetic field on the curve. You're asking how many parameters does it have? Well, it has to do with fluxes, or with monodromies. So if the curve is genus G, then you have 2G parameters. So we need to know the genus of our curve to count these moduli. Now, there is a theorem of Palansky which identifies, which actually finds the genus in such a curve. Genus is equal to the number of internal points. So, the number of moduli, real moduli of the curve is 2 times the number of internal points. And the number of parameters of the line bundle is also 2 times G. So the number of moduli altogether is 4G. Moreover, it gives us a nice view of the moduli space. There is a base of the moduli space parameterized by curves. So every point here is a curve. And then once you fix the curve, you have this, basically, you have fluxes through the different cycles in the curve. That's 2G of them. You can think of this as Jacobian. So you have this Jacobian vibration, and that's our moduli space. That has a nice height. And basically, what was important for us is Newton polygon. Once you have Newton polygon, your boundary conditions, charges, and everything else is fixed. So it's Newton polygon which determines this moduli space. If you want to go the other way, if somebody asks you to study monopole walls with certain boundary conditions, then out of these boundary conditions, out of the charges and multiplicities, you can construct these vectors. And then you assemble these vectors in order that they appear. So you order your charges certain order, so decreasing order. Then out of those you get the vectors, and then you follow first vector, second vector, third vector, and then they close into the polygon. So you count the number of points inside, you know the dimension.
Is there any interpretation for the sort of 2g minus 3 remaining moduli of the curve? Right, so if I just think of it as a complex
Yes.
G minus G curve.
Yes, I'm just
Okay.
So yeah, that's very good question. So we have internal points, but we also have this external point. So first, we finish the moduli count. The number of moduli is 4 times the number of internal points. Now the parameter count. It's minus 3. So we saw that what determines the asymptotic behavior is the root of this polynomial. And these roots are assigned to the edges. Now, first, this asymptotic data is really constrained. You know that if somebody gives you a polynomial, the product of its roots is the ratio of the leading coefficient, of the lowest coefficient, the highest coefficient. So you simply go around applying this rule, and you get the constraint that the product of all these roots has to be 1, well, plus or minus. It's just by HET theorem. Simple case. So that constrains your possible charges and positions of singularities. Also, another constraint is that this has to close into the polygon. That also constrains the charge. So once you satisfy all these charges, then you can go back and construct the curve. So this is the condition. If you satisfy these conditions for your asymptotics and position of singularity, then you will have non-trivial polynomials. So now parameters. If I give you the polynomial, the important thing was the curve and not the polynomial. So if you multiply this, you're solving g of st equals 0. If you multiply g by any complex constant, it's the same curve. In addition, if you shift your solution to the right, it doesn't change the modulus space. And if you also add constant to Higgs field, that also doesn't change the modulus space. So 3 of these parameters are inessential. So what we have is that the number of parameters is the number of perimeter integer points minus 3 corresponding to this. And you can multiply it by 3 because, well, each of these contains subleading behavior of Higgs field and 2 polymers. So you have triplets of parameters. So for each integer polygon, we have its moduli space, and now we can ask, well, when are they different? Yes, very different looking monopoles can have exactly the same moduli space. Well, on this space of curves, there is an actual transformation. So it's a curve in C star cross C star, so you can change your variables. You can send S and T to this combination, so any G to Z acts on this. You're not doing anything to the pair, line bound to the curve, but you're doing something very drastic to your monopole. So you took this curve and you wrote it in different coordinates. Now it's the same curve, but in different coordinates in C star cross C star. It takes your Newton polygon and performs S to Z transformation to it. It simply changes the basis in your lattice. But now it has very different set of charges. So if you have your charges in the asymptotic conditions, this S to Z acts on that. I would like to argue that this acts as an isometry on the modulus space. And why is that? So to generate J to Z, I need 3 generators. One is just the reflection of our coordinates. That doesn't do anything to the modulus space. I just write my modulus space with different coordinates for the monopole. T element here amounts to taking my non-abelian solution and adding a constant energy term to it. So I add something which is abelian, which is a trace part. That doesn't change the metric again. Trace part is completely determined by boundary conditions and commutes with the rest of it. And so if I consider U and monopole, I can view this as trace part SU1 monopole, it doesn't have any moduli, and SUN mod ZN solution. So all moduli in this non-abelian case. So it's a non-trivial transformation as far as the curve is concerned, but it's trivial transformation as far as modular space is concerned. And the most interesting part here is the S element of SU2Z, this one. And that amounts to the noun transform. So in terms of monopoles, it's a fairly non-trivial operation. But in every case, we know noun transform acts as an isometry on the modular space. So noun transform will interchange the role of the two coordinates here. And it, from one monopole wall, it produces quite a different monopole wall in general. So now that we have this isometry, we would like to look at, for example, all monopole walls with no moduli. In other words, we look at Newton polygons with no internal point up to SU2Z. This was also classified by Palansky. Palansky has this very interesting book. It's called Funomials. It's not about polynomials, it's about polynomials with very few terms. Let's say what. So Palansky proved that if you look at this equivalence classes up to SU2Z, then you have only three kinds of Newton polygons. You can either have degenerate one, which is just an interval, and that corresponds to constant energy solution. You can have this one, which corresponds to abelian monopole with positive direct singularity and negative direct singularity position somewhere. So in this case, two positive singularities and 1, 2, 3, 4 negative ones. But you specify basically two numbers, n and n, and this is the length of the length surface area. And there is also one U2 monowall with no moduli. So these are sort of the elementary monopole walls. They don't have any internal excitations.
Sorry, so with your abelian guy, why can't I keep it going and just add another point to the top edge?
Yes.
Right, and then just draw the same.
Absolutely. So you have to specify
so
two
you have a
integer
family.
numbers. It's
Okay.
a family
Yeah.
specified by two integer numbers,
Okay.
one less than another, and the bottom one. That's all. So that's unique here, and here you have to specify one integer number, which is just the number of integer points. No, you don't have to specify just the integer length, and you can rotate it by SU2Z any way you like. It just, if I put it horizontally, it doesn't have meaning in terms of walls. It's a rank 0 case in the So now we wanted these modular spaces, so we want something which does have non-trivial modular space, not just a point. So now we need to classify all polygons up to SU2Z, G2Z transformation, which have one internal point. Now I'm sure this problem was solved maybe in ancient Greece, I'm not sure where, but I just couldn't find the reference. If somebody knows the reference, I'd love to.
Yeah.
So I'd like to emphasize that it's not classification of reflexive polygons, but classification up to SU2Z of polygons with one internal point. So I had to do it by hand, but again, it's probably well known. And you get this list of 16. And these are this is exactly the list of reflexive polygons. That is polygon polo, which is also an integer polygon. So first there was...
if you have the condition that you have one internal point, I think in 2 dimensions it is 2%. Well, I guess you've proven it, but yeah.
Great, so you
yeah.
provide the reference. I love it. So first I was excited. I thought I found 16 ALH modular spaces which are different. But then I thought for a minute and, well, there might be another isometry text in here. In fact, thinking about this as some brain configuration helps a lot. So if you have an abelian monopole wall, its spectral curve looks like this. T is some rational function of S. Now, if you give me a non-abelian monopole wall, I can add my abelian solution to it as a trace part. I argued before, it doesn't change your modular space at all. But that's what it does. Here's what it does to the spectral curve. If the original non-invariant solution had this spectral curve, then the new solution has this thing. So now I go through my list and look at all these transformations, giving me asymmetric spaces. And I find a much shorter list. Basically, every line in my previous table contains isometric spaces, except 2. So I end up with this list. Just 8 spaces instead of 16. And then looking at this, you realize that it has something to do with toric diagrams and Betzo's. So indeed, you can match this. You can view this as blow-ups of P2. And they match to the corresponding symmetries of the subject theories, which are related to this. So you can also take a very different view of this. You can view this now as not moduli space of monopole walls. But, so first, every monopole wall, as I argued with its brane configuration, corresponds to a particular 5-dimensional Q theory. You can also realize exactly the same 5-dimensional theories by complexifying on the Betzo-based Calabi-Yau. So you start with Calabi-Yau space. You look at its canonical bundle. That has a Calabi-Yau metric. And then you look at the 5-dimensional theories which you obtain by complexifying.
So the DP634, I don't quite understand, because those guys are not toric.
That's
right?
right.
And
That's
so
right.
that you don't
You have to
mean
do-
you don't mean that the toric diagram there represents.
No.
Okay.
No. Okay, so first generically that's not toric.
Yeah.
But what you can do, you can start with P2 and
Yeah.
start blowing up points. And you have to do a few more things there to
And you have to put the blow up on top of the blow up, right?
Yeah. So we know what to do there. But it tells you how to interpret this moduli space. That you can, starting from this P2 and blow-ups, you can create a Calabi-Yau metric. And then you can interpret what we are doing as studying moduli spaces of Keller structure on that Calabi-Yau. It's not exactly Keller structure, it's sort of quaternionize Keller structure. So usually we know how to complexify Keller structure by adding B field. But now, in addition to this B field, we have 2 other fields, depending on what string theory interpretation you have. So I tried to describe all of them. But basically, in M theory, you can have flux through that Calabi-Yau of either C6 or C3. And because you have this additional torus, you can take flux of that C3 through generator of the torus and one of the P1s in that Betzo or another. So, in a way, I describe this matching. But such matching was already described before by HET and Van Doren. And in fact, they use this to match the story with asymptotic analysis. You just make a one-loop computation in SU2 theory in 5 dimensions with 2 directions complexify. So there's different interpretation of this moduli spaces that we are studying. You can think of this as SU2 gauge theory in 5 dimensions with n fundamental hypermultiples. Or equivalently through geometric engineering, you can think of this as the Betzo collapsing inside of the Calabi-Yau. It's the universal geometry is zoomed in on this collapsing side. And that gives you a local theory, and that is equivalent to that theory. And you can say that you're studying moduli spaces with such collaboration. And then the symmetry, the global symmetry of this theory, corresponds to this collapsing cycle there. Now, for my purposes, I need this to match the Newton polygon to the number of fundamentals. So in this case, the cipher corresponded to 4 fundamentals. Now that case has perimeter 8. So in general, the number of fundamentals is perimeter minus 4. So you look at SU2 theory with n massive quarks, where n is given by perimeter minus 4. The reason I mention this is I'm about to make statements about the asymptotics of these multiple spaces, and they want to match with one-loop computations of cyber. So here's cyber computation that in 5 dimensions, nothing compactified, SE2 theory with n quarks is given by, so once you look at the effective theory, it's just a sigma model. It has only one dimension, has a one-dimensional Coulomb branch, let's say parameterized by x1. And the metric on that Coulomb branch is d times dx1 squared. So this d looks like that. You can see that the leading term when x is very large is 2 times 8 minus n, the number of rows. If some directions are compactified by the same one-loop computation, so you see in Van Doren, for example, the metric is now 4-dimensional, and it has this form. So it's hyperkähler, and asymptotically this v has to be linear. So asymptotically, you can see that you get ALH type space. You have these 3 directions, they're periodic, and it's sort of Heisenberg torus. And in Savick and Morrison paper, they study this from these 2 points of view. And from the point of view of gauge theory, they get this diagram. And by analyzing their pencils, they get this diagram. And I wanted to see the relation between the two. So for us, it's just important to emphasize that this function d here behaves linearly in x, and that's the catch. So now I'm trying to understand the monopole dynamics, in particular the shape of this curve that I'm doing. It's convenient to use a little bit of biology in that, and study amoebas. So every curve has a has a corresponding amoeba. And it's this. C star you can think of as a cylinder. And another C star is another cylinder. And you get some curve in there. Now we can forget about the circles of the cylinders. Project the whole thing into a plane. This projection is the amoeba. So mathematically, if you have S and T satisfying your equation, G of ST equals 0, then you plot for such solutions log absolute value S, log absolute value S. It's exactly this projection. You forget about the phases. Amoeba was introduced by Gelfand, Kapranov, and Zelinsky. They have fascinating work. And in a way, what amoeba does, it shows you sort of the spread of eigenvalues of phi. As you go around the torus, the eigenvalues for a certain value of z, so this is z, the r direction of the monopole problem. As you move around the torus, eigenvalues of phi spread. And what's important about the amoeba is that, in some sense, it's dual to some triangulation of, or some position of Newton polygon. So these tentacles of the amoeba are orthogonal to the edges of Newton polygon. And the amoeba gets exponentially close to these linear directions. If you have a hole in the amoeba, that hole always corresponds to one of the internal points. So you just see the genus of your curve. Here, it's the same curve, it's just under the projection, this hole did not appear. So each connected component of the amoeba is convex, and it corresponds to a vertex in the Newton polygon. These non-compact ones correspond to external vertices, and the compact ones correspond to internal vertices. So, for example, it tells us how we can concatenate the monopole walls together. If I give you one monopole wall and another monopole wall, when can you glue them together? Well, in terms of amoebas, you have to sort of take one and glue it with another. And this also tells you what you should do with the curve and the bundle over it. For example, monodromy of the bundle around this direction has to coincide with one that direction. And altogether, this matches perfectly with Viro's patchworking construction, how to glue curves together, which is an approach to Hilbert's 16th problem, the way how to classify what real algebraic curves look like. Now, another way of thinking about the amoeba is in terms of the Ronkin function. If I give you a curve, g of st equals 0, you can take, instead of looking at zeros of this polynomial, you can take absolute value of this polynomial, of these two cylinders, and sort of average it over the faces. That's the Ronkin function. The reason this is good is that if you're away from the amoeba, in a way this integral misses any zero of g. If you take the gradient of this, you see that g is the denominator. So it's just purely analytic integral. So gradient is independent of where we are here. That means that on the complement of the amoeba, this function is just linear. So the graph of this function is just a plane. So you can define amoeba as a set of points where this function is not linear. If you look at the graph of this function, it looks like melted crystal. It has these planes, and then some corners are melted away. Now the slope of this is given exactly by coordinates of the corresponding point of the Newton polygon. And the height of this is given by the coefficient of the corresponding monopoles over it. Since I mentioned smelting, let me describe it in algebraic terms. It has to do with Maslow's dequantization, or tropical limit. Now, we know how to add numbers in R. Sorry, in R plus. So we know how to add two positive numbers. And that's multiply that also positive. So that you get some semi-ring operation, positive numbers. Any positive number you can write as e to the x, e to the 1. So s is e to the x, c is e to the 1. That gives us a map, it's a logarithm of R plus to R. Because you knew how to add positive numbers, you know you induce an operation on their logarithms on x and y. So here it is. Multiplication goes into addition. So on R, you have this induced operation. So these operations that we know are actually intrinsically quantum. You didn't have to write the number as e to the x. You can write it as e to the x over h, where h is any positive number. And you get these operations. Of course, they're completely equivalent. You know that we studied the same operations on our class after all. However, now let's look at the limit where Planck constant goes to 0. So what happens with this when h goes to 0? You can see that you have two positive numbers. They both go to infinity. One of them wins, one goes faster than the other. So when h goes to 0 in the classical limit, you get a new operation. Out of this, only the maximum survives. Okay? Product of the sum. So it's sort of a simple consideration, but there is Litvinov and Maslov provided this view of this. If you view this as sort of classical operation and quantum operation, then there should be some correspondence, sort of broad correspondence between statements over here and statements over there. For example, tropical geometry appears this way. Let's see how it happens for us. You have some curve and you have an amoeba. This curve was in C star cross C star. Let's write my coordinates here as x plus 2 pi h. So my circle will be size h, radius h. And another circle is also radius h. Then my natural complex coordinates are these. You can look at the Ronkin function. And now you can ask what is happening with the Ronkin function and my amoeba as I squeeze the surface. Because algebra geometrically nothing is happening. It's still C star or C star. But now you can see what's happening with Ronkin function as they decrease h. My curve shrinks. It shrinks to just these tubes of each of these lines. And my amoeba shrinks to what's called tropical variety. Right? Remember, amoeba was where Ronkin function is not linear. Now it's everywhere linear, except when the planes meet. And this tropical variety is dual to some partition of Newton polygon. So each point in Newton polygon determines a plane. The slope is determined by coordinates of the point, and the height is determined by log of coefficients of the point. The perimeter coefficients are fixed, that is, external points, external planes are fixed. And as we move along the modular space, the internal points move up and down. So we have different views. If you just look at perimeter points, you can look at these planes, and then you can say that everything above those planes is what we call a crystal. Now, if you look at this tropical limit, and you look at all planes corresponding to those external points or internal points, then you get this sort of cut crystal. There are some cut by planes. And if you look at the honest Ronkin function, then you get what they call a melted crystal. So then there is this volume which is being cut, and there is this other volume which is being melted away. So my conjecture is this, that if you have Newton polygon, it has some coefficients, internal and external coefficients. Then, if you are asymptotic, if the coefficient inside, or the coefficients inside are large, then these planes, internal planes, are very high, and this Ronkin function is well approximated by its tropical representation by just planes. Then the conjecture is that the volume that is being cut out by these planes is the Keller potential of your geometry. If you want a slightly refined version of this, then the volume beyond the melted volume, the volume under the Ronkin function, is Keller potential. So I checked just the leading term here. So the volume that is being cut is clearly cubic in the height of this plane which you cut. The cross section is dual to the polar Newton polygon. And then there is this magic formula that the perimeter of Newton polygon, or reflexive polygon, plus perimeter of its polar one is always 12. There's a beautiful paper explaining this in 3 different ways relating to it. It's really fascinating. But this fact turns out to be important for us, that we want to find this coefficient. This coefficient is this leading term and compare with Seiberg. So indeed, 2 times the polar, this coefficient here, is 12 minus perimeter of Newton polygon, so it's 8 minus n, where n is the number of layers. So this leading term is exactly the same as from one loop computation in Lewis theory. And I guess in the remaining 30 seconds, I can describe the phase structure of these spaces and how to reconcile the 2 pictures in size comparison. So if you fix boundary conditions and start varying the internal parameter, then you get various amoebas. You get a collection of amoebas. And each amoeba, or if you look at its skeleton on this tropical variety, corresponds to some triangulation of the Newton polygon. Then you have, for this Newton polygon, for example, you have 10 triangulations. And there's a plane arrangement for each of them. Now, given the Newton polygon, you can construct what's called a secondary polyhedron. And the way it happens is you number the vertices, and that will be the dimension of the space that the object will live in. Then if somebody gives you a triangulation, what you do is this, that if you want to find the first coordinate of the corresponding vector, you simply look at all triangles for which this vertex is a vertex, and count the area. So in this case, the area of this, so let's say that the area of basic simplex is 1, instead of 100. So here you have 2 plus 1. So the first coefficient will be 3. For this vertex, there's only one triangle containing it. The area of this triangle normalization is 1. So for every triangulation, you get a vector. These vectors form vertices of secondary polyhedron. This is convex object. So in our case, this will be the secondary polyhedron. And then there is a fan. So basically, for each point here, you can look at all directions which look within. That forms the fan, which is secondary fan, normal fan of this polyhedron. So as we vary our moduli, that is, as you move this plane up or down, corresponds to some motion in this space in a particular direction of that modulus. So we would like to know, when we vary our parameters, how this line changes, which cones in the fan it intersects. So long as it intersects the same set of cones, we're in the same phase. Once we go through some transition, we go to a different phase. So now we have a good notion of the phase space. What you have to do is you have to construct secondary polyhedron, look at the dual fan, and then project it onto this associahedral plane, on the plane which doesn't involve the internal point at all. So as you do this, in this case, you get this cyber picture. If you want to see this picture inside Morrison, then you simply look at this secondary fan and you look at all its cones which are looking up, which are non-associated. And that gives this. So to conclude, first we identified monopole wall charges with Newton polygons. Then we found that there is an isometry on all these Newton polygons, U to Z. The number of moduli is 4 times the number of internal points. The number of essential parameters is 3 times the number of perimeter input points minus 3. There's a reinterpretation of the moduli space we studied, the moduli space of Calabi-Yau in the extremal transitions, or moduli space of Coulomb branches of the HTs. Our conjecture, which is checked to leading order, is that Keller potential to leading order is volume of the melted volume. And the phase diagram itself is the projection of the secondary fan on the associahedral subspace. So let's stop there.
Questions?
So, this fascinating conjecture here about the Keller potential. So, is there a simple way to see that Keller what is the meaning of Keller transformations? I'm trying to say, try to say it in some geometrically invariant way. You tell me Keller potential. Or you say you're giving it to me in some sacred coordinates.
That's right.
Okay.
I gave you sacred coordinates.
Right.
This space
Okay.
can be viewed as elliptic vibration in 2 different ways.
Mm-hmm.
So a priori I have 2 sacred coordinates in this space. In fact, S and 2Z coordinates. But in these sacred coordinates, I have this ambiguity, this wrong.
Yeah, I see.
If I choose different coordinates for the same solution, I will have a different ambiguity.
Which will be some SO2G transform.
Yes.
Uh-huh.
No, which will be entirely different. It's the same Newton polygon, but different. So remember that there, curve bundle corresponding to another pair, curve bundle. Yeah, that's not S to Z, it's just I have monopole on a torus cross out. So I can pick one direction of the torus, that gives me a curve and a line bundle. Or I can pick another direction that gives me a different curve.
Mm-hmm.
They correspond to the same solution. So I have these 2 sacred coordinates as a result, with 2 different Keller potentials.
Any other questions?
You are talking about a different M theory in the symbols, so what I will hear that there's just one M theory.
Oh no, it's one M theory, but the statement is that, for example, there is one 2B theory. But if you look at 2B theory on a 2 torus, then it's equivalent to the same 2B theory, but on a dual torus, where you dualize both directions. Something similar happens with M theory on a 3 torus. M theory on a 3 torus is equivalent to the same M theory, but on a different 3 torus. And this table that I drew matches the Planck length of the first one, Planck length of the second, and periodicity of the tori in one and the other. So if one tracks the duality, then one gets more than doubly periodic monopoles and their non-transformed. One can get a whole S3Z orbit of those which one can study. And it hasn't been explored yet what they do in cage theory.
Anybody else? All right, let's thank Sergey again. Oh, sorry.
That's okay. I can ask after.
Okay.
Yeah.